Hey everybody. Sorry I can't be with you today. I'm with my dad. And so we still have a little bit of material to do with lights. I wanted to remind you that this is all available on Google Classroom. So if you aren't able to quite keep up with my pace here, you can go back to that and get any notes that you missed. But I want to make sure you have time for these and for a little activity today. So I'm going to ask that we not stop the video unless we absolutely have to here. And if you just miss anything, then spend some time tonight and get those notes that you missed. So certainly don't need to be taking notes on everything here, and we've gone through some of this stuff already. So I should have skipped ahead of that before I started the video. Oh well. Okay. Here's our focus for today. When light hits something, it does three things. We've got reflection, absorption, and transmission, and we've talked about some of these things already. Some classes have talked about more than others, but I'm only making one video, not 6 for my 6 different classes, so bear with me if you've heard this before. Consider a review. First off, reflection. That's where we have light that hits a surface and bounces off that surface. Now we got this important thing that light does when it reflects, that it bounces off at the same angle that it hits at. That'll be really important for the activity we're doing today, as well as the Secret Agent Laser Obstacle course on Thursday, and also the assessment tomorrow. That angle of incidence, it's labeled in the picture, and the angle of reflection are always going to be the same. And that idea actually gets called the law of reflection. So whatever angle they hit at, they're always going to leave at that angle. And one more representation of that with nice straight lines to represent everything. The normal that's in there, that's just a line that's perpendicular to the mirror. There's a convention that we measure from that line instead of from the surface of the mirror, but at our level it doesn't matter. It's only when you get to physics in high school that actually makes a difference. We have a couple different types of reflection. So all light hitting surfaces, we get some kind of reflection, but usually we wouldn't say, like, I can see my reflection in something. So, you know, right now there's light coming down from above me and it's hitting my face and it's bouncing off my face and going to the camera. But you don't see like a reflection of my computer screen, my computer camera in my face. So this is a result of how smooth or rough the surfaces are. So if we have a really smooth surface like a mirror, we call that regular reflection or specular reflection. If we have a rougher surface, so something that's not a polished mirror finish, we're going to have diffuse reflection. So a couple examples of the difference between these. We've got the mountain reflected in the lake down below. We see this nice clear picture, and so that would be an example of specular or regular reflection. The idea here is that because that surface is so smooth, all the rays of light that hit at this angle, they're going to bounce off at the same angle. Even if they don't hit at exactly the same spot on the surface, they're all hitting at the same, on a surface that's nice and flat. They're all going to bounce off together. The other possibility here is diffuse reflection. And in diffuse reflection, we have a rough. So with that bumpier surface, those rays of light that are hitting are not all going to behave the same way. Think of this as like the possibility of taking a bad hop in a baseball game in the infield. So if you've got a bunch of rocks and stuff out on the infield, there's a chance that the baseball will hit one of those rocks and it'll bounce off in some strange direction, some unpredictable direction. So rough surfaces, and they don't have to be that rough, just anything that isn't mirror smooth really. These rough surfaces, they're like rocky fields. We have a lot of bad hops there. So, you know, here my surface, it was bumpy, and so I have a ray of light hitting here, and maybe it hits a flat part and bounces off at that angle. But maybe this one hits kind of a bump and it bounces back off in the other direction. So the picture down here shows what happens when a nice tight laser beam hits a rough surface, and we can see that light just spreading out in all different directions here. So that's diffuse reflection. So I mean, it seems like that would be a bad thing, that it's rough, that it's bouncing off in unpredictable ways, but just keep in mind that almost everything that you are seeing all the time, you're seeing because light is hitting it and reflecting in a diffuse way. So it's not like one is better than the other. They both have their place, and we're glad that they both exist. Whenever you see something, then we have typically the thing you're seeing is either a light source, so it's putting out its own light, and that's why you can see it, or there's a light source nearby. That light is coming down and it's hitting the surface and it's bouncing off in all different directions so that people on all sides of this thing can see it. So I'm not there in the classroom with you right now, but I assume that people over on this side and people over on this side can all see the picture. Well, that must mean that the light that's coming in from the projector and hitting the screen that I'm on right now is bouncing off in all different directions here. So we have diffuse reflection going on there. Now next up, if it's not reflecting, another thing it can do is absorb. So this is where the rays of light, or the photons of light, if you have any familiarity with that term, the energy from the light is hitting the atoms and it's getting absorbed by the atoms. So it collides with the atoms, the light disappears, and instead the atoms are shaking a little bit more, or the electrons have jumped up to a little higher electric potential energy state. And so that energy is no longer light energy. Now it's thermal energy, or it's electric potential energy. So the end result on this typically is that instead of light energy, we have something has warmed up a little bit. So it's not going to seem as bright if light is being absorbed. We don't have as much light bouncing off it, making it to our eyes. And then we'll also have a warming effect. So if you've been outside on a sunny day in a black t-shirt, you've felt the effects of absorption. If you did a solar oven, your whole project was based on reflection and absorption. Let's reflect the rays of light down to our food and probably some black paper down there, and then let that stuff absorb the energy and turn it into thermal energy. Alright, so we got our puppy out here on a hot day panting away because of all that black fur. So absorbing lots and lots of light energy, turning into the thermal energy. Now, we've talked about this before, but just as a reminder, the basis for vision, the thing we need to keep in mind with this, is that you see light that hits your eye. So when we think about absorption and reflection of light off different objects, when we see, say, a red light bouncing off of, or when we see red light and we see red in an object, that's because red light is bouncing off of that object and getting to our eye. So let's look through a little bit of that with color vision and how color works. So we have all these different colors that are associated with a certain wavelength or frequency or energy level for light. Those are arranged in what we call the spectrum. Roy G. Biv is the acronym that we use for the spectrum of light. We also have ways to mix different colors together, and your brain has this sort of built-in mechanism for interpreting that. So if we see all these different colors right on top of each other all at the same time, we interpret that as white. So white isn't really white, it's just red, orange, yellow, green, blue, and violet all together, or at least a bunch of those colors mixed together. Maybe not all of them per se. Another option here is we could have no light being reflected, or very, very little light being reflected from a certain point. In that case, we would express that as black. Blackness is the absence of light. Okay. Now, as far as how we see color, we have 4 different types of cells, 2 categories of cells that we have in the back of our eye. There's this big region of color sensing or light sensing cells at the back called the retina. We have rod cells. Rods are used in low light conditions. There's only one type, and as a result, they can't distinguish one color from another. They can only tell bright from dark. But once we get a little bit more light, the cone cells start becoming active, and there's 3 different types of those, and they're each sensitive to different ranges of color. So our brain can figure out what color something is based on which of those cone cells are sensing light and which ones are not sensing light. So this graph just represents how those cone cells respond to different colors. So we have one set of cone cells that responds most to this color, so we call those the blue cones. One that responds most right here, so we call those the green cones. One that responds most right here, we would think that those might be called the yellow or the orange cones, but I think since they are the only ones that sense in the far red side of this, we call them the red cones. So blue, green, and red is what we're looking at here. And so those, as a result, end up being kind of the primary colors for light for human beings. And if we had different arrangements of cones, we would have different primary colors as well. And color blindness is just a lack of ability to distinguish between colors, and that's usually linked to missing one of these sets of cones or another. So if I were looking at something that was, say, yellow here, yellow is going to be a color that the green cones and the red cones both respond to quite a bit, but the blue ones don't. Now, if I was missing these red cones, then my brain would get a signal from yellow showing, hey, you know, the green cones are responding to it quite a bit, but there's no red cones to respond at all. If we got something like green, well, the green cones would be responding to it. And also, if we had, say, red light, well, the green cells would still be responding to that. Maybe not as much, but they'd still be responding to it. And so your brain would still be getting the same signal. It would seem a little darker, maybe, than a color like yellow or green, but it would still just be triggering the same cells. So if I were missing the red cells, I'd have a really hard time telling the difference between green and yellow and orange and red. It would all look like sort of the same color, just darker or brighter. So these little diagrams represent maybe not what it would look like to somebody with each of these conditions, but demonstrating that for somebody with, say, protanopia, where you're missing the red cones, that these two are clearly different from the other four, but we can't really tell the difference between the colors on these four. They're just sort of different brightnesses of those. So maybe this one, which looks very different to those of us with normal vision, may have 6 different colors on there. Maybe this one and this one would look pretty similar to somebody who's missing their red cones. Same deal here, but with green cones. So if you're missing the green cones, this is going to be about roughly similar to what we see here. And if we're missing the blue cones, it should be about what we see here as well. As a result of having just 3 types of cone cells that your brain is interpreting from, we can trick our brain. So for example, what you're seeing right now is not actually yellow. Our brain, our eyes, our brain together, can be tricked into seeing things that aren't there. When we see yellow, we have a response from the green cells and a response from the red cells, both. And so they both respond. They send a signal to the brain saying, hey, I'm seeing color. And the brain says, oh, well, green and red are both responding. And so that must be then yellow. Well, what if we just had a situation where we had both green light and red light present? Well, green and red would both respond. It'd send a signal to the brain saying, hey, I'm seeing light. And your brain would say, oh, okay, well, green and red are both responding, so we must be seeing yellow. So the projector that you're watching this on right now, and your cell phone screens and TV screens, they aren't actually capable of making yellow light, mostly. There actually are some TVs recently who started adding yellow pixels. But instead, they just mix different amounts of red, green, and blue. So this is a cell phone screen zoomed in really, really small. There's no purples, there's no pinks, there's no light blues or cyans or maroons, and no yellows on here. It's just red, green, and blue, mixing different amounts of red, green, and blue to get all these other colors. When we take these multiple colors of light and add them together in equal amounts, we can get what we call the primary and secondary colors. So primary goes with the types of cones that we have. We have red, green, and blue cones. So primary colors are red, green, and blue. Now if we mix red and green equally, we see that as yellow light. You can actually take a red spotlight and a green spotlight together and get yellow as a result. When I was spinning the ball around in the circle, when we saw that overlap between the red flash and the green flash, we saw yellow there. Red and blue in equal amounts gets us maroon. Green and blue in equal amounts gets us cyan. And all 3 in equal amounts gets us white. Now, this little color wheel would be a good thing to have in your notes. So let's talk about seeing objects in these colors. If I see something that is red, that means that it's pretty good at reflecting red light. And I know that it must be reflecting that light because if I'm seeing it, it must be getting to my eyes. So it has to be bouncing off that object and getting to my eyes. It's not very good at reflecting green and blue. Probably green and blue are getting absorbed instead. So if I were to take something like a red apple and put it under white light, which is a mixture of all the different colors, the red gets reflected, but the green and the blue get absorbed and they stay in that apple, so I don't see them. if I were to put it under, say, a green spotlight, that green light would all get absorbed, and so my red apple wouldn't be reflecting any light. There's no red light for it to reflect, and that's the only kind that it can reflect, so that would mean that it would appear to be, well, black. It wouldn't be sending any light toward my eye at all. If I put it under a blue spotlight, again, that blue light would get absorbed, nothing gets reflected, so it would look black to me. If I put it under, say, yellow light, which has some red in it and some green in it, the red gets reflected, so I see the red light. The green gets absorbed, so I don't see that. So the only thing I do see is the red light. So a red apple under a yellow spotlight would look red still. Another example we could do here, yellow. Things are good at reflecting both red and green. They're good at absorbing blue, so if I put it under a blue spotlight, something like a yellow banana would look black. If I put it under red, it would look red because the red light gets reflected. If I put it under a green spotlight, it would look green because the green light gets reflected. If I put it under a cyan spotlight right here, cyan light, cyan is blue and green together. Well, this yellow thing is pretty good at reflecting green. It absorbs the blue so we don't see it anymore. So all we're going to see is the green part of this cyan light. So we put a yellow banana under cyan light, and we're going to end up seeing green. If we put a yellow banana under magenta light, magenta being red and blue, remember yellow things are good at reflecting red, so we'll see that light. They're good at absorbing blue, so we won't see that, and so we're just going to see red. So a yellow banana under magenta light is going to look red to us. Now, you're probably more familiar with red, yellow, and blue as the primary colors. That's because mixing paint, like pigments, is different from mixing light. As we mix different paints together, what we find is that more and more colors get absorbed when we add more and more paint. But when we're mixing light together, we have more and more light present there. So as we mix paint, we have less light. As we mix colors, we have more light. So it's what we call mixing paint subtractive mixing, because as we put more and more into the mixture, we lose more and more light, or more gets absorbed and less gets reflected. And so the primary colors for pigment that are typically used in this model are actually not red, yellow, and blue. They're cyan, yellow, and magenta, which do a little better job at recreating more colors than red, yellow, and blue do. Which is why color printers all use cyan, yellow, and magenta ink cartridges or toner cartridges, along with the black one. We're going to skip over the phosphors. This is a cool little demo, some cool experiments you can do. I'd encourage you to watch this at some point, or just check out, do a YouTube search for phosphors. Not phosphorus, by the way, it's something different, phosphors. But these are things that are able to take in something like ultraviolet light and put out a different color. So black lights, anything that looks cool under a black light has phosphors in it. Last thing that light can do when it hits a boundary is transmission. And if it goes through at some angle, the angle will shift a bit. So we call that phenomenon refraction. Transmission just means that the light goes right through something. So if we have, say, a glass window, we have light going through, that's transmission. If you look from the outside, you probably see a bit of a reflection taking place there as well in a glass window. So maybe you can see your face in the glass window. And if you feel the window, it's probably pretty warm if it's in the sunlight, so we have some absorption going on. And that's really the way it typically goes. It's usually a mixture of reflection, absorption, and transmission all together. So just a little summary here. Reflection is when the light bounces off. And if everything bounces off of all the different colors bounce off some surface, we would see that as white. Absorption, that's where the light stops being light energy and turns to usually thermal energy. And so in this case, all the different colors are being absorbed, and so what we would see is black, because we don't see anything, and not seeing anything is the same as black. And then we have transmission here, and so this is when we have a clear object, a transparent object. We have a lot of transmission going on in that object. So that's it for the light stuff. We are now done with our new material. You're going to do a little activity today focusing on reflection, which is going to be the bigger one of the three that we have to do on tomorrow's assessment. But the assessment for tomorrow does just include all of the different things that we've learned about light, and the different colors, the different types of electromagnetic waves. All that stuff is going to be on the assessment for tomorrow. So everything that's in this overall slides presentation is fair game for the assessment. Do be sure to check this out on Google Classroom to study. Thanks very much, everybody, and enjoy the next activity.